Any questions? I guess we last left off. Where we looked at the pole going into the barn. And from the barn's point of view, the pole is shrinking, so it can fit completely inside the barn. From the pole's point of view, the barn is shrinking, and the pole can't fit in all at the same time, but it is resolved by this idea that things do not happen at the same time in both reference frames. Even though the left doors close at the same time, the right door closes first in the pole's point of view, from the pole's point of view, then the pole crashes into it, then the left door closes. All right, let's start with a little bit of Galilean relativity here. It's a car. That's a driver. All right, so if I have a car that's zipping along at 30 miles per hour. Let's go ahead and do metric. Meters per second. Generally, when you talk about how fast a car is going, it's with respect to the ground. And so I'm just going to label this as the velocity of the car with respect to the ground. That's a C and a G. This is velocity of car with respect to ground. Please, thank you for going and tracking down Erica.
You're welcome.
Meanwhile, the kid in the back seat is throwing a ball up towards his dad. And the velocity of the ball with respect to the car is, we'll just say 10 meters per second. Which is probably not bad for being inside a car. So the question is, what is the velocity of the ball with respect to the ground? And I'll open it up for conversation and or answers.
What if I said 40?
I don't know. Is that something you're likely to say?
Yes.
You want to throw some units in there?
Meters per second.
And how'd you come upon this incredible answer?
I added the other ones together.
It turns out in Galilean relativity, so if I want to figure out the velocity of the ball with respect to the ground, it's just going to be the velocity of the ball with respect to anything, plus the velocity of that anything with respect to the ground. That's supposed to be G. So as long as those two are the same, then the net result is going to be the first with respect to the second. So
in this case right here, this would be the velocity of the ball with respect to the car, plus the velocity of the car with respect to the ground. I got the last part of the first reference, or the reference for the first one is the moving object in the second. And so we do end up with 10 plus 30. I know, it's an earth-shattering concept. And then we play around with it. Once we have that first one, then, well, the velocity of the ball with respect to the car, yeah, we know what the answer is because it was given to you. But we could also find the velocity of the ball with respect to the car. Well, once I have this relationship, I know that's the velocity of the ball with respect to the ground minus the velocity of the car with respect to the ground. And whenever I'm subtracting a vector with references right there, I can just flip the vector around to change the sign. So this is the velocity of the ball with respect to the ground plus the velocity of the ground with respect to the car. So when I flip the vector around to get rid of the negative sign, just flip the object moving in the reference. And it should work. So velocity of the ball with respect to the ground, we know that's 10 because that's given. Ball with respect to ground, we found right there is 40. And then ground with respect to the car, well, I know car with respect to the ground. So ground with respect to the car has got to be the opposite. And we end up with one of those things that the math people have been pushing on us for years. Big math has always insisted 40 minus 30 is 10. And we'll go along for now. Obviously, since we're studying relativity, the rules will change. And it's not as simple as just sticking a gamma in front of it. All right, questions on this before we actually throw relativity into it? So if I'm in a rocket, I'll throw Earth into it. If the velocity of the rocket with respect to Earth is 0.9 times the speed of light, meanwhile, someone in the rocket is blasting an object, let's say throwing a ball. So the velocity of the ball with respect to the rocket, why don't we say is 0.8 times the speed of light. So if Galilean relativity were true, then, well, the velocity of the ball with respect to the Earth would be the velocity of the ball with respect to the rocket plus the velocity of the rocket with respect to the Earth. In which case, this would be ball with respect to rocket, 0.8 times the speed of light. Rocket with respect to the Earth, 0.9 times the speed of light, and I'd have 1.7 times the speed of light, which seems to violate all the other stuff that I've been talking about for the past 2 weeks, 1 week, however long. So we need to somehow account for that. So let's set up
the classic scenarios here. All right, so in relativity, you generally talk about frames of reference. This is a typical way of expressing, I drew a circle over there for Earth. I'm just drawing 2 lines to represent Earth. Earth would be, for example, here. I have a rocket cruising along at some speed u. And then I have an object that is moving along there. So this u is, call that rocket. So the velocity of the rocket with respect to Earth is equal to u. The velocity of, well, just call it a ball. Velocity of the ball with respect to the rocket is W. And the velocity of the ball with respect to the Earth, we'll just label as V. Now, when you're finding speed, it's distance over time. The trouble is that the distance and the time are not the same in the 2 reference frames. I know that the speed of the ball with respect to the Earth is going to be the distance that the ball travels over the time that it travels. And the velocity of the ball with respect to the rocket will be the velocity of, will be the distance that travels from, that is just bad notation. dE, dr, delta t, dr. Now, if you want to think back to our Lorentz transformations, I know that x prime, in other words, the moving reference frame, is going to be equal to gamma x minus vt. And t prime is going to be gamma t minus vx over c squared. And we'll just double check that, make sure I didn't do something careless there. So in our situation right here, the prime frames is the rocket frame, the unprimed frame is the Earth frame. So I'm just going to translate this into the prime notation. So this would be V equals delta x over delta t. And this is W is equal to delta x prime over delta t prime. Plug it in what we know. I got gamma delta x minus v delta t over gamma delta t minus v delta x over c squared. And let's go ahead and close that parenthesis. So W is how fast the object's moving in the rocket frame. V is how fast it's moving in the Earth frame. If I multiply top and bottom by delta t, or sorry, divide top and bottom by delta t. Oh, actually before that, gammas cancel out. So I have 1 over delta t over 1 over delta t. Then I get delta x over delta t minus v is a small problem here. That should not be a v. That should be u.
how fast the rocket's going with respect to the Earth. Divided by 1 minus u over c squared delta x over delta t. Well, delta x over delta t, that is from the Earth's point of view, how far the rocket traveled in how much time, which is just the speed. So I got v minus u over 1 minus uv over c squared. Putting it in terms of the notation we started with over on the right-hand board, this is the speed of the ball with respect to the rocket is equal to, velocity. Velocity of the ball with respect to the Earth minus the velocity of the rocket with respect to the Earth. Over 1 minus VBE, VRE, over C squared. Now this is an awkward notation right here. This is typically the way that it's presented. But one reason I put it over here is that if I ignore the bottom, the denominator, and look at just the top here, that's just Galilean relativity. So I got VBR is equal to VBE. Well, let's switch the reference frame, flip it around, plus VER. I got those two middle ones, those two middle subscripts are the same. And what I'm left with is the first one and the last one. So when you are trying to do relativistic velocities, then if you can set up the Galilean relativity, well, you've got most of it done already. So W equals V minus U is Galilean relativity, then over 1 minus, that's just the two velocities right there, c squared over c squared. So let's actually apply that over here. So the velocity of the ball with respect to Earth would be, well, I'm going to take, that's my Galilean relativity right there. I got 1.7 times the speed of light divided by 1 minus slightly different reference frames here. This is negative, that's negative. If it's positive, the other one's positive. So since I added there, I'm adding here, and this would be 0.8 c times 0.9 c over c squared. So I have 1.7 c divided by 1 plus 0.72. So I have 1.7 over 1.72 times c. And as you'll notice, this is less than the speed of light, which satisfies the stuff that we've been doing. Slightly shorter hand notation. Beta ball with respect to the Earth is equal to 1.7. Questions to here?
two velocities in the numerator, the same two velocities you multiply there, and this sign is the same as that sign. Alright, so. This will not work there. Rocket. Earth. So the velocity of the rocket with respect to the Earth. Why don't we make 0.9, did 0.9 last time. 0.7 times the speed of light. Velocity of the ball with respect to the Earth. And then the ball going that way towards it. So if that's positive, this would be negative, so negative 0.9 times the speed of light. All depends on where you sit the minus sign. We'll get the Galilean relativity right, and we'll get the rest of it. All right, so I want to know what is the velocity of the ball with respect to the rocket? Well, that's the velocity of the ball with respect to the Earth, plus the velocity of the Earth with respect to the rocket. Velocity of the ball with respect to the Earth, it's coming towards it, so actually, so this is VVE minus VRT. This is Galilean relativity right here. I don't have ER, but I have RE right there. So I have negative 0.9 C minus 0.7 C divided by 1 minus negative 0.9 C